Live. We are actually live. So thanks everybody for joining us in person the second day and remotely. I think we've really improved the Google Hangout setup. Feel free to send me emails if anything is wrong, or unmute yourself and let us know, but I think it's going to be a lot more smooth today. Basically, the agenda for the next bit is we're first going to have a presentation from Jun Kim of Georgia Tech, who's going to be telling us about Kinetic, and I'll let him tell you all about it. It's super interesting. Following that, we're going to have a series of additional presentations on NetIDE, possibly on SDX, on the pyretic packet processing library, on its querying library and or subsystem, and a path queries package that's built on top of that. And I'm also going to fill in the gaps with more information on some tutorial, some covering the code base for the pyretic test harness and maybe the topology stuff. We'll see how much time we have. So with that, I'm going to hand it over to June and mute my own microphone. I'm also turning off my speaker.
Yeah. Oh, I have to do a screen share.
Yeah, it probably is. And just make sure everyone can hear you.
Can everyone hear me?
Hello? Yeah, just shake their head if they can hear you, or raise their hand.
If you can hear me, can someone raise their hand?
There's only one.
Okay.
Thank you.
Cool. Is it shared properly?
This is good. You're not sharing your screen. We're still seeing this. So whatever's up on the screen over here is what we say. And what they say.
Oh, okay. Okay, cool. Here we go. So, yeah, I'm going to present our work called Kinetic, which is based on pyretic. So I'm going to just start with our motivation stuff. So in networking, actually, simple questions are very hard. For example, what are all the packet headers from A that can reach B, destination B? Or like, what will happen if I remove an entry from a firewall? Is group X provably isolated from group Y? Are there any loops in the network? Or what happens to the network if some event, for example, like intrusions or authentication events, occurs? And really, really like high-level questions like, why is my network slow? These are very simple questions, but actually it's not easy, and it's actually very hard if you want to like work with a network and figure the cause or things like this. So, so configuration in network configurations, these configuration files in all these network appliances defines the behavior of the network. And it provides specially for realizing operational goals. So it'll like determine how traffic enters and leaves the network. You fiddle with the network configuration to do load balancing, traffic engineering, or setting up primary and backup path. It defines which neighboring networks can send traffic, also based on business relationships and contracts. And using all these network protocols built into the network appliances, you also do like how routers within the network learn routes and scaling and performance. The thing is, like, as it has more flexibility, the complexity also increases. And the most important goal here is to actually have correctness. But the real world is actually mistakes happen. Like network operators will play within the configuration, but the thing is, like, why do we have mistakes? It's because configuration itself is very hard, and they make mistakes, and it is very common to make mistakes. This is because the policies are actually getting more complex And the configuration itself is distributed around all the routers and switches. It's not in a single place. So each network is independently configured, and there are like unexpected or unintended policy interactions going on. And so the verification problem itself is very important too. So the motivation of our work was, how do you know the network is actually doing the right thing? There are actually a lot of work, some work on this. So verification techniques, before SDN was there was a configuring verification using RCC, which is a work from Professor Nick Beamster, my advisor. And then there are also some recent works on data plane verifications, where the work could be this header space analysis paper. More recently, there was the work called Veriflow. Our work focused on the control plane verifications, and it's called kinetic, and I'll go a little more in detail what it is. So to give the overview, our work actually depends on external events, and it also one of the good things about it is easy incorporation of customized external events. So our thing is actually depends on how the network will dynamically change based on customized events. The next one is the network policies are actually expressed as finite state machines with policies, events, and the transitions between them. Good thing about this is finite state machines are actually verifiable. So we use this model checker called new SMB to actually do some verifications on the finite state machines, which are actually network policies. And the properties are checked in CTL. So the properties are expressed in this specific language called computation tree logic. And the new SMB model checker will check all these properties as you state them. So this is just a good example of a state machine and a policy expressed. And so you can see actually the vertexes here, the states are in this oval shape. And you can say it's an unauthenticated state, quarantine state, authenticated state, or clean state. And the events actually were going to trigger the transitions between states. So the events could be a failed authentication, or an infection, or successful authentications, and so forth. So as you can see, the network policies are actually represented as finite state machines, and we use this representation to feed into the new SMB model checker and verify stuff. So this is another very simple example of a network policy expressed in a finite state machine in our system. So this is an intrusion detection system. So if you express this policy in simple English, let's say it's very simple as allow traffic by default, but drop packets when detected as infected, if the flow is detected as infected. So as you can see, there's these events and policies, and they make the state machine. And the right-hand side, there's a left-hand side shows the finite state machine, and the right-hand side shows the actual code written in kinetic, which actually, this is the core code of the kinetic, and with 16 lines of code, we actually implemented this policy, and the base is pyretic. I think I should not go into details of the code, but the point is, it's really concise, and it's really easy to write these policies using finite state machines. Okay, so our project actually is able to convert. If you write your code as in the right-hand side here, it'll automatically generate a new SMB input, which can be fed into the new SMB model checker. Sure.
Go through this line by line. And if you can just repeat what everybody is, folks remote. I can go straight into you. Yeah. If you don't want to hurt, we can sort of continue with it.
Yeah.
So, okay. So there's two things going on here, right? there's like the at-sign definition, and then there's like this transition function.
Uh-huh.
And I mostly understand this. Okay, so your state machine has two variables. Vector and right?
Yep.
Okay. Now, in any state is defined by the values of these two variables table.
That is true.
Okay. So if you have two variables each with two states, you can have 4 states.
Yeah.
Okay. So now, the bottom of these two variables actually first one's a Boolean, true or false. So you basically say that its type is Boolean, initial value is false. Now the transition infected, that means, if I read this, if I understand this correctly, it means when the value of this variable changes, call this transition function.
That is true.
Is that right?
Yeah.
Okay. And now the function is above. So again, using decorators, I don't totally understand the decorator thing, like what it does here.
Mm.
So it says trans is infected. That basically means the value changes, call this function, call it infected.
Uh-huh.
But you have to write this decorator thing above it.
Yes, you have to.
Okay. I understand what that is. But then, so then the function says if some event occurred, then return the value of the variable or something. Can you read line 3 in English to me? If the value, if the event occurs, right, then return the event or something.
So yeah, it's like
almost like I know what it does. I just don't know how to read the English.
So I'm just gonna ask you to quickly summarize the question and then provide some explanations about
sure.
Folks who are remote can actually hear.
So Nick here wanted more clarification. The question was Nick wanted more clarification on the code itself on the right-hand side, especially on the third line here, where infected. This is an event, so it's an external event coming in, and it's a Boolean type. Whether it's going to be infected, it's going to be true or false. And when that event happens, it's going to call this transition function, also defined as infected, which is on the second line. And when it's called, it's going to do this. It's going to be, if it's occurred, it's going to make it's going to return that. So it's going to say that's infected. If it comes as true, the variable is going to be true. And because of that, the policy actually going to be policy in the definition in the sixth line is going to be called. So it's saying like if the event infected comes as its value with this value, whether it's true and false, it's going to make internally the infected variable as true or false, depending on the incoming. Does that make sense?
So an event comes in and it changes the value of infected, false, true.
Oops. I don't know, Josh?
Yeah.
Oh. Okay.
So it changes the event from, sorry. So it changes the event from false to true, and then that causes this function to get called.
Yeah.
Okay. And then the function says if an event occurs, then self-infect. What does that do? So like self-case. Okay. If this event occurs, then do what?
So
Self-event. Self.event. What does that mean?
So as I remember, this is like infected. So the event will come as infected, true or false, right?
Yeah.
And there's another one internally. There's a variable called infected internally, right?
Yes.
It'll make that variable as the value came in.
Line 3 does that.
Yeah. And also, this is also used to it's in this particular format so that it could be translated into a USFA format. Correct.
So then, the event comes in and then the internal variable value gets reset.
And now, because that, so then, what causes the policy function to, that's it, the transition of the infected state causes, it triggers the internal transition of the policy.
Yeah.
So where's
That is hidden. Right?
where is that shown? Like the identity value, identity variable value, like it changes from true to false.
Mm-hmm.
And now what triggers line 6 to 8?
6 to happen.
What triggers
That is just hidden. It just is going to occur.
How do you write that? How do you write the change in the policy, the transition in the policy state depends on the transition of infected.
So you say in the 7th line,
7th line.
the self case.
Oh, I see.
Is that variable infection to the
Yeah, because it goes
So basically, you can kind of do these transitions. These transitions are not like being called. Like these functions aren't like being called by anything explicitly. You're just writing them down as relationships almost.
Yeah, it's
You kind of think of it as like always being executing.
it's
not how.
so if you see on the left side, there's exogenous and endogenous, right? So this exogenous function transition is actually caused by an external event, and internally, if the infected variable changes, it'll call the policy. Sounds good, or?
Basically.
Yeah.
I still don't fully understand line 3.
Yeah. Well, so
anyway, it's like.
If you want, I can provide potentially a little bit more.
Yeah.
Yeah.
So line 3. Can we just go back to that?
There's some magic food going on.
I sort of understand that it's basically changing the value of the internal variable. I just don't understand how this impacts that.
Oh, so okay. How this works exactly? In terms of, so there's going to be a variable infected that's going to be affected by this function. Okay. So when we define the FSM definition, actually we give variables different names. So this thing is actually declared as a FSM variable. So we're looking at line 11 right now. And the FSM variable is defined in terms of having a type. So this is a set of values that it can take. So maybe that's a Boolean, which is true, false, already built in. Or maybe it's a new type, which is created. That's just a set of policies that are allowable, like as on line 14. The second thing is, what is the initial value that it's going to take? And the third thing is, what is the function that's going to describe how that variable's behavior changes over time?
Oh, okay.
So the infected variable is actually created over here within this FSM definition. Now, the transition function, which we give the same name as variable by convention, basically has its own specialized syntax. So what we created over here was a little DSL. So that way, whenever you wrote the transition functions, that you guaranteed to have, that you guaranteed to be directly translatable to USMV. Right. And so what all of this is it's really just creating a bunch of cases. So on line 3 is one case with a condition, and there are a set of allowable conditions you can create. These allowable conditions are tests on the variable itself, on the value of the variable itself, whether an event with the name of this transition occurred. So if the event handler gives him something that's called an infection event that it receives through the JSON interface, then it says, oh, that's self.event. This is, and occurred is like, did I get one? So occurred is one condition. You can also have is true, the variable infected. Or you can have variable infected equals, some value if, say, the variable infected actually took 3 integer numbers.
So self there refers to basically the transition.
It refers to the event named infected, which is the same name as the variable. So we make sure the variable name is the same as the event name. And this at transition decorator is what lets us know that, hey, this infected thing, self.event, is the event named infected. So this at transition decorator basically takes in this definition as a function, inspects what its name is, and then takes that name and uses it to fill in the self.events. So that way we don't have to write like it occurred infected for each transition function we write. We might want to refer to self.event many times for different reasons in several different cases. So this is sort of the general purpose mechanism doing that. If you look down at definition policy, you'll see, oh, self case is true. The variable that's named infected. And here we actually have to use infected as the other variable name, because the only thing we know about a priori is that there's a very local policy.
So in line 3, like I find line 3 just the most confusing. So like,
sure.
Is the value of some internal variable set there?
So the way these transition functions work is what they have a series of cases. Each case has a condition, and it has a return value. And so whatever case you match, and whatever the return value is in that case, that's the next value that the variable will take.
Okay. So how are you returning as a value?
So self.event is how are you returning?
Because that's some JSON thing. Like, right, and now you're saying like, okay, that return that value. That's the next value for the variable. How do we go from self.event?
Yeah, so self.event is actually not the string infected. Self.event is the value of the most recent event that came in, whose name was the same as that of the transition function. So this is the value of the infected event which just occurred. And if no infected event occurred, then running occurred on that value. So it's a little bit messy. It might be a little bit. Yeah. Yeah, and this, it might be a little clearer to actually say occurred self.event and do this self.event.value. I think that would probably be more sensible.
That would be like a little more intuitive.
Yeah.
Because otherwise it's sort of like you're setting the value of a variable like in a pen.
Yeah, totally. I mean, this code basically got hacked out during the rebuttal period. We had like 2 days to get it working. So yeah, so the great point.
Like that part's not super intuitive. The other thing where you're sort of like testing, where you're setting the values in the policy function is pretty straightforward.
Okay.
Just find the other part confusing.
Yeah.
Okay. So yeah, we'll work on making that.
Yeah.
Awesome.
Alrighty. Okay, so I'll continue. I don't know whether, okay. So this is the conversion, which is auto-link generated. If you put in the policy, programmer puts in policy, this will be automatically generated and put into the new SMB model checker. And based on the CTL properties you wrote down, it'll check whether it's true or false. So this is some examples of CTL.
Can I go back to that again?
Sure.
I just want to read this.
Sure.
Actually, I guess you never have to write this, but like I'm curious.
Yeah.
It looks very close to the code.
Yeah.
Just no accident, right?
Yeah, it's not.
Okay, so I know you explained this to me last week, but like I mean, so okay, so can I just read this out? Okay, so you have 2 variables, policy and infected. Policy can take 2 values, either identity or drop. Infected is Boolean, either true or false.
Assign, those are initial values. Initially policy is identity, initially infected is false. Okay, so now next policy, it says these are transitions. So this says the next value of the policy variable is, well, if the case, okay, so if it's infected, if the left side is true, then okay.
So if infected is true, then the next value of policy is wrong.
Yeah.
Otherwise, identity.
Yeah.
So now
This is where the next value is infected, right?
Yeah.
Okay, so this is true, then false or true. That line, I don't fully understand what's going on. 15, like. I
I understand. It's basically saying depending on the value, it could be false or true.
But you already know that, right? So that's what confuses me, like, because you already said in like line 4 that infected is a Boolean. So I'm like really confused about line 15.
Why do you even need it?
Why do you need it? Yeah.
So I'm not sure about the precise syntax of USMD.
Yeah.
It may be that if you don't provide a transition function,
it
automatically just does true, false, true. But what we have done is created an automatic translation from whatever the kinetic model was to something which is correctly USMD. So that's not necessarily going to be the most compact representation.
Right.
In fact, if you look over here, right on line 16, we clearly translated.
16 makes total sense.
16 might make total sense, but it's not useful because we'll never hit that case, right?
Yeah. It is.
So it's not the most compact representation.
This is like the set of allowed. These are the set of allowed transitions.
Yeah,
it's not like
given that your value is the infected state, the only place you can go next is drop. And that's when you must.
I understand. This is not like a
specification. This
is not a specification of what should happen. This is a specification of what should be allowed.
What can happen.
What should be allowed? What can be allowed to happen?
Yeah, exactly. If you don't have that line, the knowledge checker thinks this. Oh, there's going to be no transitions. They'll just stay there. Stay there in the unit, right? It'll just stay there false, and it'll say, okay, it'll just stay false, so never transition to true.
Yeah, and so this, in fact, this captures the non-determined in the events.
Yeah.
Right? At any point in time, like if we're infected, we could become infected.
This is the exogenous part of the stuff.
Yeah,
this captures the fact that there's an exogenous transition. I get it now. Yeah.
So
right. Okay. What you just said actually, I think, made it a little more clear, which is like at any given time, it could be either one of these things.
Yeah. Exactly.
Because otherwise, if you don't have that, then the only transitions that are allowed are exogenous.
Exactly.
Because it's like, okay, affected is what it is. It is what it is. There's nothing. Yeah. Okay.
Policy is determined by that. So there's no exogenous. There's no variability in the policy in of itself. It's only variable insofar as infected might change.
I finally understand what line 15 is for.
Okay. Yeah, I guess that's a cleaner explanation.
Well, I think the way you said it was like, at any time, this value could either be false or true.
Yeah.
And if you don't have that, it doesn't capture that the value could actually take either of these values at any point in time. If you don't have that, then there's no way to have an exogenous transition. The exogenous thing is what's causing the value to change at arbitrary points in time.
Yeah.
It's outside the state machine.
Yeah. So when USMP is actually
very clever.
Yeah, without that line, it will not even check these, like when it goes to false, true or false.
Yeah.
All right. So these are some examples of CTL. So, like left-hand side, I'm not going to go like really into detail, but you can just say like left-hand side is saying like if infection event arrives, then the system should drop the packet. Low policies drop. The next line says if it's cleared, should be identity, which it will allow the packet. Third line is say from any state it is possible to go to allowed state again, which is also very important stuff that you know that you can actually be allowed again based on events. Fourth one is saying for all paths, policy allows packet until an eviction occurs. So these are some syntax you have to know in CTL, but it is possible to express a lot of good properties and check them with the new USMP checker. So briefly in the relation to pyretic, it's built on top of, kinetic is built on top of pyretic. It uses a dynamic policy class for dynamically updating the policies. And of course, it ultimately returns a pyretic policy to enforce everything on the switches. And it relies on pyretic interpretation of compilations. Yeah, this is just a brief overview of how the architecture, how it's built on pyretic. I guess I'll not really go into detail, but you can see there's external events. So pyretic runtime is underneath, and we have external event processor up there. And I think I'll not go into what everything is.
Pyretic runtime can also cast events. So you can use the pyretic query on topology.
Yeah, exactly.
Those can be events. Kinetic also adds to that an additional.
Exactly. Kinetic kind of like listens to all these events, whether it's coming from pyretic or external.
You might want to, by the way, take the event driver code that you guys have done and maybe turn that into like a new pyretic submodule that's usable for like everything.
That makes sense, actually. Yeah.
Because that was really nice contribution as well.
I think people actually very use it in different ways, actually. So.
Yeah. I think we even had some people who just took that piece of the code and used it for force projects and generators and use that. Yeah. Cool.
All right. So I think I'll skip this part over time. So what we need from pyretic, so performance. So I thought this is kind of like important for us too. Like I think SDX had similar problems with performance sometimes. So on compilation time and rule optimization, I think we can have some improvements if possible. If there's like new operators or constructs, which will be helpful for real-world network policies, I think we can also make use of it if they add it in pyretic.
So what's the new operators here? What kind of new operators we need?
That we have to discuss. I think we did have some discussions on it, like what kind of it's not just sequential or parallel. Or I think Nick had this also about subsumption. Remember?
Yeah. So we kind of had that delta update operator.
Delta update operator.
Ended up kind of given that. Although I don't think we kind of removed that from the paper because it was just too much to fit in.
Yeah.
But and I think this delta update operator relates. It's like the compilation techniques for that and disjoint parallel actually.
So one question I have is network operators. Do they need to write policies in pyretic, or there can be a way in which they can write the way they are using some ACLs in different ways? They are defining the policies values in the campus network, which can be translated to pyretic. Is there?
So building technology for doing automated translation of currently existing techniques to
Pyretic.
That's a super interesting open space to explore. I mean, some things, right, like Cisco IOS, it's known that Cisco IOS does not have a well-defined syntax and semantics. I mean, it's just it's a problem. There's no definition of the thing, and it's literally ill-defined.
Is it true that there's no grammar? I've heard conflicting reports on that. Anyway, it's totally
so I'm not enough of an expert.
Okay.
I know there are projects that don't a whole lot of work on trying to take iOS configs and turning them into something coherent. Leveraging that work to then do an automated translation to pyretic would be really cool, in my opinion. Trying to do it from scratch would be really painful, in my opinion, but also very cool.
So this is the feedback one which for SD. For now, the policies are defined in pyretic, but in the long run, we don't expect the participants to get excited about writing their policies in pyretic because they are already writing some different formats. For now, they're writing in BGP configs and stuff. So if there is some way of translating their different policies in pyretic policies, I don't know what's the solution here.
To make sure it's not so good so that they'll just keep doing it.
Well, I think Kinetic's a lovely example of building abstractions on top of pyretic that to some extent hide a lot of what pyretic's doing, right?
So that's customize abstractions that need basically, right? Campus network policies. Exactly.
You go from assembly to C, and then you use C to build Python.
Something which Flowlog did.
Yeah.
Something which Flowlog did was integrated different ways in which you express policies, database and all. They integrated everything together, and then you translate to the network policies.
Yeah, so actually, Flowlog translates down to network.
Right.
Ultimately. So.
Yeah.
They don't implement on top of pyretic, they implement on top of a fork of pyretic-camel that uses the last working version of pyretic-camel's variant of netcore. Pyretic-camel now uses in cat, but there are problems. I don't know. Like, that's as much as I followed the discussion on their development board. Yeah. But, it got complicated. So
I can imagine.
Yeah.
So yeah, just
if we can avoid that kind of complication by, with the community discussion, we had yesterday really kind of creating processes where people go stuff on. I read it. They provide us a regression test that the team then uses to like make sure we don't break other people's stuff. That would be that. I think that's definitely the way to go.
Yeah.
And there'll be more discussion about that upcoming. I email and whatever.
Yeah, I think it's good actually.
Okay, just to summarize, this is the Kinect webpage. If you want more information, we have a GitHub cluster, which is a separate branch of pyretic. Please contact me if you want more information. Thank you. Thank you.
It seems like one thing too is like you can only verify. We talked about this, right? You can only verify independent.
Yeah, we do that. I think we have to work on that.
So
Are there logics that like you can post?
you have to go in like 10 minutes, so you want to give a presentation. Is
Uh,
that what's going on? I saw you standing up.
no, I was just getting my charger back.
Because I can stop asking questions.
No, go ahead.
But okay. So, are there logics that let you sort of verify composed state machines? That would be kind of interesting if there are. If not,
I think
maybe it's time to talk to
It might be time to talk to Sharad.
Sharad, right?
yeah. But the best thing will be that if you're able to specify like specifications, like verification specifications for individual applications, and then you do the compilation, and it can automatically verify the entire policy system.
Yeah. So there's certain types of compositions for which you can do that kind of verification. Like a very simple example, which works as sequential composition, where you're composing something with a firewall.
Right.
Right. When you do a load balancer system that modifies packets and you're sequentially composing that with something else to independently verify their properties, it's not necessarily system. It's system in corner cases. And that's, based on my recollection of thinking more deeply about this about 6 months ago. So this is not breaking my mind, but it's definitely an interesting place to get in. A really cool direction to go. Sharad seems to feel like there might be some, neat and interesting things to do there. So we can, try to get that conversation up and running if somebody's interested in taking point on this forward.
So another sort of, I had like other comments about like things that you could like ways to extend it in different ways, like, and some of this I think I mentioned to you in like an email, but I'll just probably didn't read it. So like I'll repeat it. So one is like basically where this stops is it'll tell you basically like can a certain pyretic policy be reached, right, in your state machine, but it doesn't tell you like what's going to happen as a result of that pyretic policy. So you could say like, oh, I'm going to reach this. Will I ever basically, reach a state where like pyretic policy like mumblefoo is implemented, but you don't know if like mumblefoo is going to create a loop, right? So it seems to me that there's still like some gap there where it's like, well, you want to close this with like data plane kinds of questions, kind of like the stuff that like HSA and Veriflow is saying, where I actually want to say, is there a set of like, actually like, to put it in a positive thing, like you could say, if there's an intrusion, I actually want to make sure this part of the network gets partitioned, right? Like, I want to create like a air gap equivalent, right? And that's a data plane question. But I'm wondering if like, is it as simple as like, can you basically, maybe it's not interesting because maybe you just take CTL and take your pyretic policy and compile it and run HSA on the compilation.
The problem is the CTL has a lot of states, most likely. And so what you need to do then is you're going to need to run HSA or whatever on each one of those states.
Right, which is huge, right?
States,
and then each one of those actually has a huge number of packets on which you can run symbolic execution.
Exactly.
So it's really a scaling problem.
It's a big selling point. Now the question is,
But
can you leverage stuff you know about higher level language, that higher level exposure, you can do better.
Yeah.
And so, for example, you can do a cantrip that pyretic-miniconf-session-3, which relies upon pyretic flood, which relies upon fixtures algorithm, calculating these minimum static trees, always maintains and activity. And you can prove that it goes along the way it maintains activity. And then you can use that. Basically, what you can leverage is you can leverage the property of flood, which is known, it's based on fixture, to analyze the kinetic version of the map learner to show that every time there's a steep transition, connectivity, the previous connectivity is preserved. And since you know at the initial state you are connected, and you know that every transition preserves connectivity, then you now show for every single state, every descending state has the property of the initial state with respect to connectivity. Oh, that's awesome. You didn't have to actually analyze every single state independently. So it may be that there are ways to extend.
It's almost like an induction or something.
What?
It's almost like an induction.
Exactly. So you can inductively or incrementally prove for additional states a property that you can prove to one spot using a heavy mechanism. Then you're good. Then you're in the computational tractable space.
Yeah. That seems like a really interesting, like, next paper or something is like coupling control plane with data plane verification. I mean, Flowlog does some aspects of that, I think, but not really. Not really what. No. No.
It's not doing that.
Okay.
I don't. I think there are.
I don't think they do exactly what I'm talking about here. Like,
I think there are more limited variants of that which they can do.
Yeah, because you can ask certain kinds of data plane questions, like certain.
I can, but it's been like 2 months since I even skipped the paper. My brain is just full of information right now. Cool. So, time-wise, you guys probably have to run now,
Yeah. Definitely.
Okay. So just quickly, anyone else have any questions for Jim or about kinetic?
Can shoot me an
Okay, great. So get going, guys. Thank you so much for your time.
Thank you.
At this point, maybe what we're going to do is we're going to switch over to Pedro, who's going to tell us if he's around and amenable. He's going to tell us about net ID for that. Does that sound good?
Here we are. Hello. Yeah. Can you hear me now? Hello. Can you hear me?
How's it going? I can hear you.
Okay, fine.
Should I mute my microphone?
Yes.
Okay. Just do a screen share because right now we just see like a bubble bed.
Okay, I'm sharing the screen now. Do you see it?
No, we don't see it right now. I can see it on my finger. Oh,
Hey, Josh.
Yeah.
Can you?
You can introduce yourself.
Okay.
Yeah, totally. That's kind of weird. For some reason, I'm not seeing it.
Let's try again.
Someone else is? Oh, I know. Don't worry about it.
I'm trying again.
Yeah, give it another try. Oh, also, I don't see your face when we do the.
I see.
Yeah.
Did you click on it? Yeah, I think it might take time to.
Safe
Are we ready?
You going back to Atlanta? Enjoy.
Very fun.
Yeah.
It's just weird. It's not showing up on mine, it's showing up on everyone else.
Oh.
Maybe you can rejoin your own Hangout or something.
Yeah, I wonder if I'll stop the broadcast slide. So what I'm gonna try to do, I'm gonna try to hang out with
I can't barely understand you.
Or just plug into his laptop.
Yeah, that's another thought. Yeah, it's maybe a better thought.
Well, the only thing is the record's happening through time. Yeah, sure.
Oh.
But I think you could. Oh, right. That's the point. Yeah.
Okay. Hey, Pedro.
Yes.
Can you leave and then quickly rejoin and see if that helps things on my end?
Okay, I'll try that. I'm
Thanks.
just going to, which means I say. Hi. Hello. Now try screen share everything. How is it now? You're muted. I can't hear you.
Yeah, sorry. We're just going to switch computers that are attached to the projector because I'm still having the problem. But we'll just assume that things are going to work right on the recording. And yeah, and then you'll go ahead and present. So just give us one moment on our side.
Okay. How's sound?
Are you the projector actually?
Yeah, well, you were doing good there.
I'm more or less ready here, so.
Okay, cool. So yeah, so I'm just click on Pedro's. So Pedro, at this point we can see you.
What do you?
Screen, the NetID stuff. If you can give yourself a brief introduction before you start the slides, that would be awesome.
Okay. Hello. Good morning for you. Afternoon for us here on the other side of the pond. I'm Pedro Aranda. I work. Well, now it's more or less 25 years that I've been with the research and development lab of Telefonica. Currently I'm the technical manager or the technical coordinator for this project called NetID we're doing here with the funds of the European Commission. Just to share a bit of history with you, today marks the 79th anniversary of the fascist uprising here in Spain, which actually depleted the country of all kinds of intellectuals, and some very, very bright people, irony of things, ended up at Princeton. So it's sort of a special day for me. And now, after having said that, and hoping that you can listen to everything correctly and that the sound is okay, I'm just going to full screen the presentation and talk a bit about this crazy stuff we're doing here with SDN in general. We wanted, our lemma is to try to empower the S in the SDN. So all the software aspects in SDN are important for us as an operator and here in Telefonica. And so we started this initiative to see how we can make software techniques enter the whole network running and network creation business. Short agenda, just the problem statement, what our approach is, then first steps, and here I'm going to talk a bit of the crazy stuff we've been doing with Pyretic, some words about who we are, and sort of a conclusion. So problem statement, I think you all know more or less this one. We are in a situation where there's lots of different SDN, open flowish, non-open flowish stuff. You see there are lots of different possible systems you can work with, and when I get a new student here with me and he comes in with a grant, I just make him look a bit at the landscape, and he comes up normally with something like that and with a crisis. because he really doesn't know what to do with all these tools. More so, we have a proliferation of SDN frameworks, so there's no solution that fits all. There are several things there that don't really fit. And finally, we have key services for integration that are still missing here. What is the approach we wanted to take with that? So the concept is, well, this is what we said and what we sold in the short version to the commission, so aiming at delivering a single point of entry, blah, blah, blah. So the long version we tried to make people aware of is that we need a control and gear-independent approach to support development of network applications. We want an integrated development and tool support for all the network design cycles, so that we really have an S in SDN environments. And we want new network layer services and support for emulation in the loop, simulator in the loop, and stuff like that. So in one picture, this is what we want to do. You have on top a sort of a developer kit with editors, repository where we can really look at storing applications we write, so that we are not continually reinventing the wheel. And then we also have here an application configuration, application deployers, some development tools, and then we have something we called here the network application engine, which is basically I have different network applications. Then I have an interpreter, and then I can go and make those applications talk to different SDN platforms, be they either a native OpenFlow API, some specific controllers, or even third-party and proprietary controllers. This including things like tools like resource management, garbage collection, profiling, and debugging in the network. So if we succeed, what we will get? If we succeed, what we will get will be an integrated development environment for SDN. So hopefully this will lower the entry barrier for SDN application developers and make our market a bit more lively. Second thing, we want to be controller agnostic, and we aim at a controller agnostic platform that drives SDN. So as a network operator, because Telefonica is a network operator, we want to lower vendor dependency. We are not going to be running from one vendor to the other and just selling our soul to any vendor. The other thing is that at this point in time, SDN applications we have are not reusable. So what we want to have is SDN applications that become reusable, so that we write once, and following more or less what the Java people said at one point in time, deploy nearly everywhere. And on the other hand, we also want to provide a variety of tools that are, if possible, controller agnostic for the SDN ecosystem, which we think are really important. Things like debuggers to check errors during the programming phase, and then SDN profilers to ensure that the performance of your SDN application is the correct one. Who are we? Who is this bunch of crazy people on this side of the pond? Well, we are Telefonica and in their networks here in the center in Madrid, in Spain. Then we have people in France, Thales near Paris. We have people from Intel working in Ireland. We have the project coordinator, who is a CreateNet in the northern part of Italy. And then we have Fujitsu Labs and the University of Paderborn in the Federal Republic of Germany. So, first steps for this has been running since January this year. So we already have done our first steps and found our first problems. But what did we have? We are going to what we want to get is a controller agnostic environment. So at this point in time, you have a single app that manages your network with a single OpenFlow controller. OpenFlow. We are centering on OpenFlow and concentrating on the OpenFlow protocol and OpenFlow switches. But what we see and what we have not yet been able to do is having a single network application that manages the network, even keeping OpenFlow as the southbound interface if you have different OpenFlow controllers. And notice that here I'm not speaking about mixing SDN southbound interfaces, so we are just concentrating on a specific version of OpenFlow, for example. So one of our partners in the consortium, the IMDEA people, had some experience in pyretic, and they told us, hey, why don't you just take a look at pyretic? Why? Because if you take a look, this interpreter we sort of thought of somehow resembles what you guys have been doing. And by the way, this what I heard yesterday about moving and evolving the interface between the backend and the controller client. This is something we need to be informed. Okay. So one of the first things we thought is, hey, let's try and write a second client here. So we took the Rio controller, which is another SDN, another OpenFlow controller, which is also written with Python. So why not try to make this work? So what we actually did was, since we could decouple pyretic from POX, we wanted to go and couple pyretics into Rio. So we produced this controller. With this, what we have done is identify commonalities in both platforms and identified the little common programming patterns there are, and we have also been able to really take a look at the different programming paradigms you have and if they can be reconciled or not. Why? Because what we have is a completely disconnected SDN working environment where you have different pyretic. We have a pyretic program that runs on the POX framework and on the POX controller. You have Rio with the framework and the controller. You have Beacon, and you name it. What we want to do is actually having the different programs, try to convert them to a common external SDL that then is transformed into the different applications we run on the different controllers. So this transformation has a couple of steps and a lot of challenges. So we start by the source, which is on one side we have the different source code, the network applications written either with pyretic, Beacon, frenetic, or whatever, and we have the network configuration on the other side. And then we want to at least give a try to having some sort of northbound composition that provides an intermediate language. We call this intermediate representation format IRF, where we actually compose the different applications and we get at the end a description of the behavior of the application, and on the other hand we also have some IRF data we need in order to deploy the application down in the platform. And then we are also going to try to have a southbound transformation here, so that we go from different platforms, the POX platform, the Rio platform, and etc., and then deploy those things in the different controllers. What are we doing with IRF? Actually, with the IRF, what we are doing is trying to abstract different controller features. And we are also trying to have a concrete topology that goes and is used, although we are trying to abstract the concepts we are using. Problems we see, or questions, or how open issues still is if you have the application written for a specific platform, how are we sure that the things we are deploying down in the controllers behave like the source applications? And the other big challenge we have right now is how can we transform arbitrary code into this IRF. We are trying to give first try at the pyretic code, and it seems to be working. But we are trying to generalize this, and we think that in the future we might have to confront arbitrary code, and we are still looking at how we can go and explain this code here and express this code as our IRF. So, as a short conclusion, we see still a lot of fragmentation in the landscape, and that is deterring new entrants, and basically when we speak to some students, which come to our company with grants, and other people who in the universities and similar environments, what these people are mainly deterred from is because there's a steep learning curve. Then because many people feel that you design once your network application, then you have to write it many times, and at the end it's never going to be executed in the real life. And because there are people who come with a lot of software development experience, and they miss necessary development tools like real good debuggers and profilers and stuff like that. NetID is trying to tackle this problem by offering a rich and unified network application develop environment, which is at this point starting to be developed and is written using Eclipse, and is going to be integrated into the Eclipse. And so what we want at the end of the project to show this is that we could regain this write once, execute anywhere paradigm for SDN. If not anywhere, then in lots of places. Then we also want to provide next generation application development tools, namely profilers and debuggers for SDN applications. And by decoupling this pyretic stuff, which is extremely interesting for us, and being able to run one application on different controllers, we have first initial evidence that our approach is not completely unrealistic. Of course, we did when we prepared the proposal, we went for maximums, and we are starting to see that we are going to be doing compromises. But I think at the very end we're going to have an environment which is going to be quite interesting for network operators. This is a NEU-led effort, so we are not alone on this, and we have knowledge from different parts of the SDN ecosystem who are contributing into that. So we are not only developers, but we are not only developers in this consortium. We are also having users, and we are bringing in some users like, in this case, me, or the operational units in my company and in Thales and in Fujitsu, who are going to be looking at the tools and doing some proof of concept implementation of different environments and use cases we've defined in the project. I invite you to follow us. We have a wonderful web page where we are starting to provide information. This capture is old as old can be, because the web page has really evolved a lot. And anyhow, if you want to contact me, this is the old address, still working. But so when you send me an email and I reply, you'll see my new address. Sorry for that. I should change it to our new addresses in the telefonica.com environment. And when I send this, I can share the slides. So when I send them to Josh, I'm going to correct this. So that was it. A very quick run on our project. Any questions? Any reactions?
Okay, so I've unmuted my mic, and it's generally now pointing at the video of here doing that. Wow, now I've muted my own video, so now I don't understand how that works.
No, you're good.
Am I good?
Yeah.
It's not showing up on my computer either. My computer's just a mess.
Hey, Pedro, thank you. This is Jen. I have a quick question. So a number of these software frameworks have fairly different models of how they expect the programmer to interact with the underlying network. So I was just curious, when you put all these things together, how do you think about what kind of abstraction you're giving to the programmer? Should I think of it as a union of all the different platforms, or should I think of it as something that's, I guess I'm struggling to get my head around how does the programmer deal with the complexity of all the different models of the network that these different tools give? Is there some unifying framework that they go in?
We are, okay, so of course, taking into account everything and all the possible solutions is impossible, because there are platforms that are completely impossible to integrate. Anyhow, we see that at least if for a first step we are able to get the controller agnostic platform with Pyretic, and then this would be a first step, and then we are going to start selecting other controllers or other frameworks which might have interesting how could I say interesting features that may fit more or less with Pyretic. So this is the idea. We are not going to. We are, of course, when you bid for a project, you say you're going to be completely holistic, but then reality kicks in between, and you have to really look into. You really have to start doing compromises. Anyhow, if we are able to get a second or a third environment, and have a subset of features, of common features there, and we are able to look at the different possibilities and have a unifying model for a subset of features, that would be a real great environment for us. But again, just decoupling and being able to run the same application on a couple of controllers, from a network operator's point of view, we have completely covered our objectives.
Great, thanks.
What kind of different southbound APIs, like you mentioned Fox and Ryu, are you only considering kind of like OpenFlow based southbound APIs, or are you like considering a broader range of southbound things?
We are quite interesting question. So first of all, we are looking at being OpenFlow version independent, so that we can sort of encompass the different versions of the OpenFlow protocol in the southbound. And then we are also looking at some promising solutions which are out there, like Loxygen and other platforms or other solutions that are giving us a sort of abstraction of what is happening in of what is happening there, so that we can also try to integrate some proprietary solutions.
I see. So, yeah.
So at this point in time, our main
Loxygen thing.
Yes, this is our first candidate at this point in time.
Is that already, like, I guess that supports like a number of different versions of OpenFlow already? Yeah. Okay, I see.
Yeah, that abstracts you.
What about these like Exxon, Yang, all this other stuff that people are talking about on the?
We are looking at Yang as part of this concept of the IRF, so where we are going to store this abstracted version of the applications. We are going to use as much Yang as we can, and netconf and SNMP are in the roadmap of this Loxygen stuff. So we think we are going to follow that and see how far they progress with that, and what kind of abstractions they give us to go for netconf and Yang solutions. SNMP is already part of Loxygen, so we are also looking at that.
Cool. I met this guy Alec Leckie last week.
Yes.
I think he took my course in Ireland there. He was saying that you had a code release coming up or something. I mean, it might be useful to kind of like test some things out.
Yeah, well, I mean, one of the things that we are releasing right now, that all the licensing issues in the consortium. You see different partners, different licensing problems, and so on. Now that everything is cleared, we have the Rio backend and the Rio client, which are going to be released shortly. And then we also have the University of Paderborn, who is our main IDE developer, and they are developing a full set of plugins for the Eclipse development environment, and they are going to be releasing all that kind of things. But at the end, you have an integrated development environment which is released. We're going to be releasing that privately. It's going to be open sourced.
Cool.
Any other questions? Yeah?
Question.
I can't. I don't understand you. I can't hear you. Something happened.
Hey, how about now?
Better.
Okay, good. I accidentally unplugged the microphone.
Minor problem, right? So in one of your slides where you had different languages going up at the top, and then there was the middle shim layer that you guys are handling, and then POX and Rio. So the middle layer, is that static, dynamic? Because most of the languages have large amounts of dynamic features. How do you go about handling that, or is that not there yet?
It's let's say we have a concept out there that is that handles dynamic features, but it's still a concept. It's still
Okay.
very shaky. It's just coming up.
Fair enough.
So,
Yeah.
but we are the people from Paderborn. They have lots of experience in using MapeK and other sort of paradigms, and they said they were giving a try at having all the dynamic features done in MapeK and this kind of things.
Okay. Sounds good. Thanks. Anyone else?
Okay, well let's thank Pedro again.
Yep.
Thanks.
What we're going to do now is take a maybe 10-minute break, and then we'll come back with a little bit more presenting. Also, lunch for those of us who are here should be arriving in the not too far future. And yeah, so everyone, please take a stretch. Those of you at home, I'm going to be sending out another link on the mailing list, 5 minutes before we get started, or maybe more. So we'll look forward to seeing you all after a short break.
Okay. Bye.
Bye, guys.